Hello everyone, this is Meghna Rangarajan from RV College of Engineering. Today I'm going to try to explain how a brain-computer interface can be used for neuroprosthesis. So even with all the technological advances that we see today, people with spinal cord injury still face a lot of lifestyle challenges. People with tetraplegia still face a lot of difficulties with carrying out their basic day-to-day activities due to their limited hand usage. Wheelchairs do provide some motor capabilities to these people, but then they still face a lot of limitations when it comes to steps and stairs. However, when we talk about restoring their motor capabilities, there is a question that arises as to how we control these. Many people might not be able to control it with their hands. So this is where a brain-computer interface comes into picture. So this provides means of hands-free control of various electrical devices. What is a brain-computer interface? So think about controlling all the electrical devices around you or influencing your environment just by thinking about it. So that is what a BCI does. A BCI is a computer-based system that acquires brain signals, analyzes them, and translates them into commands that can control or influence your environment. Here, the user and the BCI system, they both work together, undergo a lot of training so that the environment is influenced based on the user's intents. So, a lot of physiological signals can be used in the BCI system to control the devices around you or your environment. So, the first one would be a scalp EEG. What exactly is a scalp EEG? This is a postsynaptic membrane polarity changes which can be caught by placing electrodes in strategic positions on an individual scalp. This might be the safest option when it comes to using neuroprosthetics using a BCI, but then it has its own disadvantages. One, the main one is that the signal undergoes a lot of attenuation as it has to pass through the dura, the skull, and the scalp. So most of the information might be lost. So this gets us to the second signal that can be used. So this signal is captured by placing microarrays in the cortex of your brain. So this also has its own disadvantages, but then this can capture more accurate signals. But then the disadvantages are that this has a high degree of invasiveness. That is, the person has to undergo a neurosurgical procedure to implant these microarrays in the brain, and it covers only a small portion of the brain. So that is the disadvantage. So that gets us to the third kind of signal. That is the ECOG based BCI. What is an ECOG? ECOG is an electrocorticography or an intracranial encephalography. So this is again captured by placing electrodes in the brain, and the person does have to undergo neurosurgical implantation. But then the main advantage of this is that it can capture a large area, signals from a large area of the brain. So what are the components of a BCI system? So a signal acquisition hardware, feature extraction, feature translation, and device output constitute the BCI system. So these four components work together and is controlled by an operating protocol that defines all the minute details that is involved in the BCI system. And this protocol must also be very flexible so that it can adapt based on the user's needs. Let's see what each of these components perform. Signal acquisition, as the name suggests, it involves the measurement of the brain signals using a sensor, and it can be a sensor placed on the scalp or intracranial sensors, as we just discussed. These signals are later filtered and amplified so that it can be processed and is converted into a digital signal so that it can be fed into a computer. A feature extraction. The digital signals that have been obtained are then processed and converted into a form that can be suitable so that it can be transformed into output commands. These features also must have very strong correlations with the user's intents. Feature translation. The signal features that are then passed on to a feature translation algorithm, which converts the features into appropriate commands for the output device. The translation algorithm must again be adaptive, so that it can adapt itself to the user's intents. The device output, which brings us to the final component and the main intent of this entire procedure, that is the output devices that are being controlled, which can be a cursor or a letter selection or a robotic arm or anything and so on. The output from these devices are later fed back to the user, which closes the control loop. So whatever we just discussed is explained in this block diagram now. So the human brain, and then the three different procedures that are involved in extracting signals from the brain. One is the scalp electrodes, which gives us the EEG. One is the arrays which are placed in the cortex of the brain, which gives us the ECOG, and the electrodes placed within the brain, which can cover a larger region of the brain and extract signals from the larger region, which gives us a much simplified version of the brain signal. Any signal obtained from any of these methodologies is then converted into a digital signal and then fed into the signal processing unit. This signal processing unit contains the feature extraction and the translation algorithm. So as we just saw, the feature extraction converts the digital signal into features which have high correlation with the user's intents. The translation algorithm converts these features into signals which are suitable for controlling the output devices. The output devices, which can either be the neuroprosthesis, a robotic arm, letter selection, anything, or a cursor movement, or any such thing, is controlled by the signal obtained from the translation algorithm. The output from these devices is again fed back to the human brain as a feedback, so that this is a closed control loop system, so that it can adapt based on the change in the user's intents or the environment. What are the existing electrophysiological BCI systems? So these classifications are based on the different types of signals that are used in the BCI systems. So the first system is using the scalp recorded EEG. This, as we just saw there, is a very non-invasive procedure, and it just involves placing electrodes on the individual scalp. But then the limitation is that it can only lead to a very low degree freedom movement. But then this can be used in neurorehabilitation. What is neurorehabilitation? So people who have suffered with stroke do experience limitations in their motor functions. So this can be used to restore their motor capabilities. And this, assisted with functional electrical stimulations, may also aid motor relearning in stroke patients. BCIs that use ECOG activities. As we saw, this is not a very minimally invasive procedure and involves neurosurgical procedures of the implantations of the microarray. But then this does produce a better output, and as it reads better, more accurate signals, and is more practical when we are talking about long-term usage. BCIs that use activity recorded within the brain. So this is based on a clinical trial that has been carried on patients with tetraplegia. A microarray is placed within the precentral gyrus of the patients. The images to the right show the microarray which is being implanted and the region of the brain where the microarray is implanted. So this has demonstrated very good results when it comes to controlling a robotic arm or cursors or lights and televisions and etc. And has been stable for more than 100 days after the implantation. So what is the future of BCIs? As we discussed that there are many applications when it comes to implementation of BCIs in neuroprosthetics. But then there are certain aspects that has to be improved so that this implementation can be smoother and more useful. So we are going to discuss three such critical areas, one of them being the signal acquisition hardware. All the BCI systems, as we discussed, are very majorly dependent on the sensors that are being used. So if you're talking about the EEG based BCIs, then the electrodes that are being placed should be dry electrodes. They must be small and portable, and also must have cosmetically acceptable mountings. They must also perform well in all kinds of environments, and this might be a little difficult at this stage. If you're talking about the ECOG based BCIs, they still have to undergo a lot of research to come up with a array which is safe and minimally invasive. The second area being validation and dissemination. So if we are talking about releasing BCIs into market and using them for actual clinical purposes, then these two are the very important questions which need to be answered. How good can the BCI get? So these the BCIs which are being released must be optimized, and their limitations must be very well defined. The second question being, which BCIs are better for which purposes? So as we know, there are different kinds of signal acquisition hardware which are being used. One being placements of electrodes on the skull, and the other one being the neurosurgical procedure involving the microarrays. So we must know what kind of patients require what kind of arrays, and so this must be very clearly assessed. The third region being the reliability. So here, the brain-computer interfaces must be suitable for every real-life application, and they must be as reliable as the natural muscular-based actions. So this problem depends on recognizing these three fundamental issues: the central role of the adaptive interactions of the BCI operation, the desirability of designing BCIs that imitate the functioning of the normal central nervous system, the importance of incorporating additional brain signals and providing additional sensory feedback. So these three questions must be answered for us to get better in this critical area. So that gets us to the end of our presentation, and these slides just give us an information about what all papers are being referred for this seminar. I hope you guys got a brief idea about how a BCI can be implemented in neuroprosthetics. Thank you for your patience.